is it to have Tashi Walde here today to speak about higher categories and quantization. Okay, please.
Yeah, thank you very much. Thank you for inviting me and being here to have this to give this talk. So yeah, today I want to talk about a subject which I find quite interesting, and maybe I can convince you that it's interesting, which is higher semi-additivity, and with a particular focus here on the quantization of gauge theories, even though that's not sort of the main part of the work I do, but that's sort of where this is maybe more can be motivated a bit better. Okay, so let me start with an introduction. And for this, I want to briefly say a little bit about topological field theories. So yeah, for me, a topological field theory, so this is sort of a T.S. Siegel formulation of topological field theories, is something which associates, let's say, to each n-1 manifold a vector space, and to each cobordism between such manifolds, it associates a linear map. And so an example is you have like this pair of pans, and then this manifold on top gets sent to Z of S1, which is some vector space, and then this pair of pans gets sent to a linear map from the tensor product of these two to this. And so, and in particular, maybe an important part is that if you take a closed manifold, then this closed manifold you can view as a cobordism from the empty set to the empty set. And so this will be a homomorphism from Z of the empty set to Z of the empty set. And we also require Z of the empty set to be the complex numbers. And so this is just a number in C. And more precisely, maybe to summarize all of this, what one would usually do is collect all of this data into what is called a symmetric monoidal functor from a category of bordisms to a category of vector spaces. So this is not going to be super important for now what exactly this is. This is more like to set the stage what sort of objects we're talking about. And more generally, of course, one can look at TFTs, which are valued not in vector spaces, but in some arbitrarily sophisticated gadget, let's say with values in some symmetric monoidal infinity n category C. If you don't know what that is, that's not so important. So maybe I should put a disclaimer also at this point. So many of the things which I'm doing, their natural generality usually lives in some infinity categorical world, like usually in infinity 1 or infinity n categories. But I will try to sort of, most of this talk I will give in a way where even if you have no idea what that is, if you just think about ordinary categories, you will be well served. And if you do know what infinity categories are, then maybe you can sort of see what I'm hinting at. So let me now say what I mean by gauge theory. So for me, a gauge theory is the following. And so this, of course, is motivated by physics, which I cannot say I understand that much. But so I'll sort of take this as a mathematical gadget, which I can sort of study on its own. And so let's say G is a finite group. Of course, gauge theories also exist for non-finite groups, but in this talk, I'll focus on the finite case. And so a classical, and by classical, I mean unquantized, we will then later see the whole point is to somehow quantize this finite gauge theory. We can think of it as a topological field theory, but which doesn't associate something to the manifold directly, but which needs the additional data of a principal G bundle. So what this does is for each manifold M, we don't yet get a vector space, but we only get a vector space once we specify a principal G bundle. So for each principal G bundle, which is then maybe looks like this. And I mean, in general, one would ask a flat connection, but since the group is finite, this is no extra data. And for each such principal G bundle, we get a vector space. vector space, which I call maybe Y, and to denote that it depends on this P, I'll write Y of M comma P. And then this should be functorial in the vector, in the G bundle. So for each isomorphism, so whenever I have an isomorphism between two such G bundle, then of course I also want the corresponding vector spaces to be there to be a chosen isomorphism between them. And then of course there should be some compatibilities, like if I compose such isomorphisms, then also these isomorphisms should compose. And one way of summarizing this is that the data I associate to the manifold is not a vector space itself, but it is a local system of vector spaces. So all of this data, I can say this is a local system of vector spaces indexed by the groupoid of G bundles. So let's call it ban G of M. But concretely, this is what it is. And similarly, I won't spell it out, but similarly, also the value on Bordisms is not just a number or a linear map, but it depends again on the choice of a principal G bundle on the Bordism. And so a way to summarize this, which for now is still, which I will make precise a little bit later, what exactly the objects are appearing here, but one can summarize this by saying that we have a symmetric monoidal functor from some suitable symmetric monoidal category of Bordism to a category which for now I'll just denote like this, and I will say a bit later better what this is when somehow the time is right. And so this is a suitable, I guess, in full generality, infinity n category of local systems. So to each manifold, I don't just associate an object, but actually a local system. And maybe this M, oops, sorry, this M gets associated to Y of M, which I can think of as a local system on this groupoid of bundles. And so now I'll just state the goal, and then don't worry, I will give a very explicit example of this so that maybe if you're not very familiar with these objects, you can have a very concrete example in mind throughout the talk to help you sort of go along with the things I explain. And so the goal of all this story is to quantize such a classical gauge theory to obtain the quantized gauge theory, which is then an honest TFT. So it doesn't take values in this local systems, but in C directly. So we have somehow this thing which depends on this additional data of the vector bundle, and we somehow want to integrate over these vector bundles so that then it loses the dependency of this vector bundle by somehow averaging over all vector bundles at once. That's one way of thinking about this. And the strategy, which is somehow explained in work by Fried, Hopkins, Lurie, and Teleman, is the following. So they write a very nice expository paper about this, but unfortunately, many details are lacking, so that's why there's one still has to do a lot to actually fill these. Is the following idea: so that for certain suitable infinity n categories, which we'll see what that means, we just compose our original unquantized version with a certain symmetric monoidal functor, which for now I'll write like this, which goes from this category of local systems to really C itself. And I'll just write down a formula which for now doesn't make any sense, but which we will make sense of in the rest of the talk. So it will be some sort of sum, or maybe if you want, you can write this as some sort of integral, but maybe let me write this as a direct sum. So this will be some sort of direct sum indexed by this groupoid of bundles, of the value. And note that this is not a set. This is really something non-discrete. So this is not just the ordinary direct sum. So we have to make sense of this. So there are three things I will try to tell you in this talk. The first thing is what suitable means. So we need to define this. So this will be the first part of this talk. Then we need to make precise this formula. What precisely do we mean by this, and why does it behave in a way which justifies this notation? And third, we need to construct, or at least I won't, of course, be able to give the details, but give you the idea of how you would construct this functor. So these are somehow the three things I will be talking about in this talk. And so, yeah, so this is somehow the outline. And now to give you a thing to sort of wrap your head around while you follow along, I'll write down a running example, which I very much advise to keep in mind through all of this, especially if maybe you're not so familiar with all the abstraction involved. So the running example is like very baby example in a sense. And this is because it's very trivial, but it's also the first step where already something interesting happens. So I think it is worth keeping in mind. And so this is just one-dimensional gauge theory associated to a character. Sorry, why? I don't know why my screen sometimes jumped. To a character. So we have a character of our group. So that's just a group homomorphism to the unit complex numbers. And associated to such a character, there is a finite gauge theory, which is described as follows. So I'll not give I won't give the full description. I'll just tell you what it does on the point, which is somehow the only real zero-dimensional manifold, and then what it does on the circle, and then everything else is more or less specified. Okay, so the value on the point, and more precisely the positively oriented point. So I haven't said this, but usually these Bordisms, they carry on orientations and so on. But these are all things I want to sweep a little bit under the rug because they're not that important for the main thing I want to talk about in this talk. So what's the value on the point? Well, on the point, there is a unique G bundle, which just looks like this. It's just G together with a map to the point itself. And this G bundle, we just send it to a vector space, which we just choose to be just C, the complex numbers themselves. But now, of course, this vector space, it is unique up to isomorphism, but it has some automorphism. Namely, whenever you multiply with a group element, this gives you an automorphism of this, sorry, I said vector bundle, I meant G bundle. And this automorphism, we just send it to the multiplication with this character. So in other words, this y of a point, we can really think of it as the one-dimensional representation of G associated to this character. So it has one vector space, and then for each group element, it has an automorphism, which is exactly given by multiplication with this character. So this is just the representation. Okay, so this is the value on a point. So on a point, it is just this character as a representation. And let me also tell you the value on the circle, because that's also where something interesting happens. And then later, we will see throughout how all these things appear when we actually explain higher semi-additivity. So the value on the circle, which we think of as a Bordism from the empty set to the empty set. So first of all, a bundle, a principal G bundle on the circle, there is a unique one of them up to isomorphism. There's a unique bundle, which let's say we call PG, P small g, for each element of the group. And this is the bundle. It's the unique bundle which has holonomy G. So there's one bundle for each group element. But some of these are actually, sorry, I said there, yeah, some of these are actually isomorphic. So there are in fact some isomorphism between some of these. So every group element H gives me a bundle isomorphism between the bundle associated to G and the bundle associated to the conjugate. So H minus 1 GH. So in other words, we have here the bundles are indexed by G, but then there's some sort of redundancy where some of these are actually isomorphic and we can keep track of them. And so the value on the circle is now not just a single number, but it is a number which is parametrized by this groupoid. So we have a map from this groupoid of bundles to C, which just sends this specific bundle PG to lambda of G. And this is a well-defined map because the character lambda G is well-defined up to conjugation. So this makes sense. So you see that somehow the value in a circle is already a relatively complicated object which has to do with the conjugacy classes of the group. And then on each conjugacy class, you even have some automorphisms. Okay, so keep this example in mind, and now we'll come to the main part of the talk. And so let me start by introducing semi-additive and m-semi-additive categories. So for here, so an infinity category, I'll denote, I'll abbreviate for infinity 1 category. Okay, so this is these are definitions which go back to Hopkins and Lurie, and then this was worked out quite beautifully by Harpas. And so the first part is still classical, and then the second part is really the interesting story. So an infinity category, or just category, just think of category, is called semi-additive. And this should be a notion which, even if not explicitly, should be at least implicitly familiar to many, also called zero semi-additive. If, well, first of all, it has a zero object. So 0, and this means that for every other object X, there exists a unique morphism from X to 0 and a unique morphism from 0 to X. And additionally, for any finite set S, and for any family of objects X from S to C, we have a product indexed by these objects and a coproduct. And finally, we want that this coproduct and this product coincides. And this will be the general feature of higher semi-additivity, that we have a certain limit and a certain co-limit, and they will be required to be identified by a certain canonical map, which in this case one can write very explicitly. So we have a canonical map theta from this coproduct to this product. And this has components. So to give a map from the coproduct to the product, I just need to give a map from each of these factors to each of these factors. And this will just be, well, if S is equal to T, then I just take the identity. And otherwise, I take the zero map, which makes sense because by the previous axiom, I have a unique map to 0 and a unique map from 0, and I can compose them. And this map should be an equivalence. And using this map, this equivalence, we identify these and then just write the direct sum symbol. Okay, so this should be relatively familiar. There are many, many examples which you will have seen, namely, for example, vector spaces over a field, modules over some ring some spectrum, or any derived category, and so on and so on and so on, any category of representations. So if you have done any sort of algebra using categories, most likely the categories which appear will have been semi-additive and in fact even additive. And there's one important lemma which I want to mention, namely that automatically from these axioms, it follows that the HOMs carry an addition. So if you have such a semi-additive category, then there is an addition. And in fact, a unique addition. Unique if one requires the usual properties. It needs to be associative, commutative. It needs to distribute under composition. The usual things you would like for addition to be true on morphisms. And I'll just tell you how you get this, because then you will see the parallel when I talk about higher semi-additivity. And so let's say you have two morphisms from X to Y. And how do you define their sum? You want to go from X to Y. And so what you can do is you can first go with the diagonal to X cross X. Then you can apply F and G in each coordinate. And then there's this equivalence from the coproduct to the product, which you then can go backwards and then take the co-diagonal and go to Y. Or equivalently, you could have first used this equivalence and then used this on the coproduct. But in any case, you see that this is this formula then describes F plus G. And you can check that this actually defines a unique an addition which has all these nice properties, and in fact it is even unique with all those properties. Okay, so this was now classical semi-additivity, and now I want to talk about higher semi-additivity and what it has to do with quantization of field theories. And so to do that, I first have to tell you a little bit more about a special class of groupoids. So let S be a groupoid. So remember, a groupoid consists of objects, and then between objects, I have isomorphisms, which I can compose. That's a category where every morphism is invertible. And if I have such a groupoid, then one thing I can do is I can form pi0, which is just its set of isomorphism classes or of equivalence classes of S. And such a groupoid is called zero finite if it is up to equivalence, let's say, a finite set. So what does this mean? It means that any two objects in this groupoid, they are either not isomorphic at all, or if they are isomorphic, then that isomorphism is unique. So in other words, if I look at the isomorphisms from X to Y, so this notation here, S, X, Y, is just the set of isos from X to Y in S. So this is supposed to be either just a singleton or empty. So either there's a unique way of identifying them or there's none at all. And additionally, it's supposed to be a finite set. So the set of isomorphism classes also has to be finite. So this condition here assures that it's equivalent to a set. So up to equivalence, we can just think of this as being a completely discrete groupoid with just objects and no non-trivial isomorphisms. And then additionally, it has to be finite. And then additionally, we call it one finite if the first condition is the same, if pi0 is finite. And additionally, each set S, X, Y is also finite. And now I just want to do a slight edit to this for if there are people in the audience who know about infinity groupoids. So one can also do the same for infinity groupoids, and then one can define a slightly, one can define this for all M. So I can define M plus one finite groupoids by just saying the same thing. The set of isomorphism classes is finite, and then each of these is no longer a set, but a groupoid. And this one is supposed to be M finite, which makes sense recursively. So if you don't know about this, you can just safely ignore this. And in this talk, I will mostly talk about one semi-additivity, which only involves one finite. But you see that actually the definition of n+1 finite is exactly the same, just that one has to sort of use this recursive nature where between any two objects x and y, I don't just have a set of isomorphisms, but again a groupoid, and so it's recursively makes sense to ask for this to be finite. And so here's the example you should have in mind. And again, if this was all a bit confusing, then please just keep this example in mind, and it's good enough for most of the things I'm talking today. So the example is, let G be a finite group. Then we have a groupoid which is called BG, and I've drawn a picture of BG. BG is a very simple groupoid. It only has a single object, and then the automorphisms of that object, so the isomorphisms from that object to itself, are just the group itself, and then these can be composed just by the group law. So this is a groupoid with a single object and G as its automorphisms. And this is in fact a one finite groupoid. And in fact, any other one finite groupoid is just equivalent to a finite disjoint union of such. So if you just care about one finite, basically these are the only ones you really have to think about. And these are in fact the ones which we have already implicitly seen above, even if maybe this wasn't very explicit, and I will spell it out. Okay, and now we can come to the main definition of this talk. So a semi-additive category is one where it makes sense to take direct sums of objects indexed by any finite set. And now M semi-additive is the same, except that you're allowed to take direct sums of objects indexed not just by a finite set, but by any finite groupoid. And what this means is spelled out in the following definition. So an infinity category C is called M+1 semi-additive. So this is a recursive definition where I say, okay, first of all, it has to be M semi-additive. So if you just think about, if you just want to know what one semi-additive, then here you just have to start with 0 semi-additive, which I recall just means the ordinary semi-additive. And then additionally, for every M+1 finite groupoid, or infinity groupoid maybe, S, and for each functor from S to C, there exists a limit indexed by S and a colimit. And let me spell out what this means in the case of the groupoid we care about, which is BG. So in the case in the example where C is vector spaces and S is BG, then such a functor BG to C is just the same as a representation of G. It sends the unique object of BG to a vector space, and then each automorphism to the action of the group. And then in this case, the limit is just the space of invariance, and the colimit is just the co-invariance. So this is maybe the thing you should have in mind. And then there's one more condition, which again is exactly analog to the semi-additivity I explained before, which is that this limit and this colimit need to agree via a certain specific canonical map, which I can write down. And so this has to be a map from the colimit to the limit S in S, T in S. And this map is given by essentially the same formula as before, just written in a slightly more fancy way. So I have a sum which is indexed by all possible isomorphisms between S and T. And then I can apply X, which is my diagram, to this path. And since this is a functor, this will give me an isomorphism from XS to XT. And I take the sum over all of these. And now I need to explain what this sum is. So by definition, this here is M finite. So the original S was M plus 1 finite. So by definition, this is M finite. And again, if you just think about M equal 1, then this is just a set. So it's just 0 finite. So this is just an ordinary sum, and you don't have to explain anything else. In general, you have to explain what it means to take a sum over an M finite groupoid. And this you can do by the analogous lemma to the thing I explained before. So this is somehow recursive. If you know that it is M semi-additive, that allows you to define a sum up for an M finite groupoid, and then that allows you to write down this map, and then asking this map to be an equivalence gives you M plus 1 semi-additivity, and so on. So this canonical map is an equivalence. Okay, and the lemma is the same as before. So I'll maybe just go over it. This is not so important, but so the morphisms, they admit sums indexed by an arbitrary M finite groupoid. I.e., whenever you have a map which in your HOMs is indexed by an M finite groupoid, you can form their sum, which is the sum which appears, for example, here. And the way to do it is exactly the same. It's literally the same formula. I'll just write the exact same diagram as before, where it now just looks a little bit scarier now, but it's really just the same, just that instead of product you have and coproducts, you have slightly more general limits and colimits. So you go from X, you go into the diagonal, then you apply component-wise, then you go back along this map, which is an isomorphism, and then you go back. I just want to write this so that you see that a lot of this story, it's really just sort of writing the same formulas again and again, but like with a slightly different interpretation. Okay, so here's the upshot of this story. In an M semi-additive category, the main thing you should remember, if you don't remember the exact definition, that's not so important, but the main thing you should remember is that in an M semi-additive infinity N category, there are two things you can do. You can form S-indexed sums, where S is an N finite groupoid, both of objects, in which case we will denote it as a direct sum, and of morphisms. And that's the upshot, that you can sort of sum objects and morphisms in a sort of non-discrete way. So these sums now don't just make sense when this is a set you're summing over, but even like a groupoid, for example, BG. And let's come back to our baby example to see what happens here. So we saw that vector spaces is always zero semi-additive. And now let's talk about one semi-additivity. So one semi-additivity, we would have to see that for example, given a representation, we have to compare the co-limit and the limit. And I already told you that the co-limit are just the co-invariants, the limit are just the invariants. And if you work out what this special map is, which I wrote down above, you will see that this is just the sum of the action of all the group elements. And this is the so-called norm map. And in general, this norm map is not an isomorphism. But it is when the characteristic of the field is good. So, for example, in the complex numbers, everything will be fine. So if the characteristic is good, then the inverse, so if the order of the group doesn't divide the characteristic, if the characteristic doesn't divide the order of the group, then you have an inverse map, which is just given by multiplying with 1 over the group, the order of the group. And so the upshot of this is that, for example, vect C is in fact one semi-additive. And in fact, it is also semi-additive for all highers for like trivial reason, because it is an ordinary category. So these higher conditions, they don't even appear. And let me also tell you, so I told you what the sum on objects is. It's just the invariance or the co-invariance respectively. And let me now tell you also what the sum on morphisms are. The sum on morphisms is also something one can just write down explicitly. So let's say you have a groupoid S, and you have indexed by this groupoid, you have a homomorphism. Then the sum S in S Fs is just going to be the sum, which is indexed by the isomorphism classes of your objects, of your groupoid, Fs. But then each of these has a weight which depends on the automorphism group of that object. So on the automorphism in your groupoid from X to itself. So this is what comes out if you work it out, and we will see in the example of the Gauge theory. Okay. Okay, so I've now introduced the notion of higher semi-additivity, which I will say once again, allows us to sum both objects and morphisms, not just over finite sets, but over arbitrary finite groupoids, which are finite up to some certain dimension. And now comes the second ingredient. Which has to do with matrices and how to interpret matrices in this context. So one thing which you probably know from linear algebra is that morphisms between direct sums can be always written as matrices. So if I have a hom from one direct sum to another direct sum, then an element in here, you can always think of it as like a tuple FTS, where FTS goes from XS to XT. And this tuple is now indexed by T in T and S in S. And now the only thing to keep in mind is that this tuple is now no longer just a discrete tuple indexed by a set, but it's somehow, yeah, you can think of this as somehow a non-discrete matrix. But of course, if your S are just sets, then this is just an ordinary matrix up to the fact that you didn't choose an order on the columns. But yeah, so this are just usual matrices when S and T are sets. Up to, again, of course, you didn't choose an order on the elements of the set. So if you actually want to write it down, you should choose an order. But you can compose these tuples just with the exact usual composition law of matrices. So if you have a tuple like this and you want to compose it with a tuple like this, then you just write down this formula, which you would write down in linear algebra. The only different thing is that now this sum is one of those, not discrete sum, but it's a sum over a groupoid. But again, you know, this same thing works exactly. And we can use this idea to freely turn any infinity category into a semi-additive one by somehow taking formal sums. And I want to explain this, and then this will lead to the desired quantization. So we want to start with an infinity category C, and we want to turn it into an M semi-additive one. And so we have C, and we want to have a map to a new category, which I'll call free M of C for now, where heuristically this free MC looks as follows. So it has objects, it has formal direct sums, formal M finite direct sums like this. And then morphisms are matrices of formal sums. And again, this matrices has to be interpreted in this sort of groupoid indexed way. And so we have a matrix where each entry is a formal sum. index by some by some group point MTS. And now let me give you a slightly more formal version, and then you will somehow see that we come full circle and that this matrix interpretation actually has something to do with the things we started with. And so more formally, one way of thinking of these matrices is as follows. So now you say the objects, well, you want this formal direct sum. You can think of it concretely. You just say, okay, this formal direct sum is a pair consisting of an m-finite groupoid together with a local system in C, which then this is the local system which you then sort of think of as this formal sum. And the morphisms are the following. So let's say you have one such object, so it's an S together with a map to C, and another. Then what is a morphism? A morphism is a decorated span. And by this, I just mean it is another m-finite groupoid M, which maps both to here and to here, and such that there's a natural transformation F in this square. And why is this the same as a matrix? This is maybe the main thing to keep in mind from this thing, is that you can think of this as a matrix by saying, well, what is the matrix entry at the point t comma s? Well, if I look at t comma s, sorry, this should be a t. If you look at the point s here and the point t here, then you can look at all the points up here which map down to s and to t. So that will then be this MTS. These are all the points in here which map down to this corresponding little t and little s. And then for each m up here, since you have a natural transformation, you will have a map in C from x of s to y of t. And these are the maps you're summing over. So this is somehow the informal interpretation as a formal direct sum of this thing, which is a maybe more rigorous thing. Okay, and I don't have time, unfortunately, to explain this in much more detail, but you can compose such spans by just, so if you have two such spans, you can compose them by taking a pullback here, or to be very precise, a homotopy pullback. And then you can compose these natural transformations by pasting this diagram. Okay. The upshot of all of this is that these spans, they form an infinity category, which we call like this. So this is the infinity category of m-finite spans decorated in C. And this is the category of local systems which I have, which appeared in the introduction. So this is the target of the quantized, of the unquantized TFT. Okay. And so now comes the main result, which in this case is to harp us for in this one-dimensional case, is that this category is indeed the free semi-additive infinity category generated by C. And what does this mean? It means that this is semi-additive, and if I have any other semi-additive infinity category, M semi-additive, then there is a unique functor. So sorry, whenever I have a functor like this, and then there is a unique semi-additive functor like this. And in particular, this is how we get the quantization functor we want. So if C itself is already M semi-additive, then you can just take the identity, and then this will produce a map like this, which we call sum M. Which informally just, so remember the objects here are just formal direct sums, And we can just send each formal direct sum to the actual direct sum, which exists in C because it is semi-additive. Where informally, sum M sends formal direct sum to actual direct sums. Okay, so let me erase this because and now I'll draw the last picture, which shows the actual how the quantization comes about. So the classical gauge theory, as I explained, it is a functor which goes from board to the span category. And now we have produced this functor sum, which interprets each of these objects as a formal direct sum and then sends it to the actual direct sum. And then this composite, this is then our quantized gauge theory. And so let me tell you what this does in so we started, when exactly did we start?
3 past.
Okay, so I will give this example, then state the last conjecture and then stop. So this example is maybe to bring it all a little bit more down to earth again. So what is it associated to a character lambda? So in this case, we have to define the value of the quantized version at a point. It should be this sum indexed by this groupoid BG over this X. And we saw that this sum in this case is really just the invariance, or equivalently the co-invariance, sorry, of X. Which, of course, in this case, since this is a one-dimensional representation, is just either 0 or C, depending on whether this character is trivial or not. And the second expression, now one has to use this other formula where you have to sum over all the principal G bundles on the circle, lambda G. And now I don't have time to do this computation, but if you just write down the formula, which I explained, then essentially what you're doing, you're summing over conjugacy classes indexed by some centralizers. And this is a well-known character formula that this is equal to either 0 or 1, depending on whether the character is trivial or not. So this is the centralizer. These are the conjugacy classes. And this is exactly the dimension of Z plus, of Z of the point, which is what it should be. So the value of the circle should always be the dimension of the value of the point. And so this is somehow what we expect. Okay, so I wanted to say a little bit about the outlook to higher dimensional, because remember here, we only really talked about one-dimensional gauge theory, but there's, so this is now the work in progress, which I just want to briefly mention. It is very much work in progress, but I'm very happy to discuss this a little bit. Yeah, so I will skip the more formal definitions. And so this is work in progress with Claudia Scheinbauer. And so basically there is an analogous definition of a M semi-additive infinity N category. Oops, sorry. So let me just maybe say like this, but it's, you know, you just write down something similar. And yeah, we still don't know how to best write this very conceptually, but we have a good working definition of this. And let me just give you an example, maybe that's more helpful. since the time is somehow short. And so the example is we take a category called alg. This is a 2 category whose objects are some suitable algebras over C. So let's, for simplicity, just say semi-simple. This works in more general, but just to be safe, let's just say simply simple. Then the morphisms are bimodules. The hom from A to B are bimodules. Over A and B, and the composition is just given by tensor product. So if you have a bimodule M from A to B and a bimodule N from B to C, then you can compose them just by tensoring them over the middle algebra. And this is a 2 category, and it is in fact 1 semi-additive. Again, I had prepared a little computation to show this, but I'll skip this. So let me just state the final conjecture so that it is at least on the board. So for each infinity n category C, we have an infinity n category which is span n mfin C of local systems, which is defined in a very analogous way as just before, just that we now not just have spans, but also spans of spans. And the conjecture is that this exhibits the latter as the free M semi-additive n category, infinity n category generated by C. And in particular, we get the following picture, which is the one I want to conclude with, which is somehow the quantization story. So we have, it's the same picture as before, but now not just in dimension 1, but in all dimensions. So we have finite gauge theory here. So this is unquantized. Then we have the identity here. And then by the unit, since if C is M semi-additive, we will get a sum functor here, just like before. And then by composing these, we will then get the quantized finite gauge theory. Okay, so on this note, let me end my talk, and let me thank you for your attention. Maybe I'll leave this up because it's somehow the main diagram.
Yeah, thank you very much, Tashi. Do we have questions or comments? Raise your hand or show yourself. I have questions, so maybe I make a start. So I have a vague question and a concrete question. Maybe I start with the concrete one. So you started out with something about these G bundles, and then we went to spans, and then it was a theorem then that these spans are actually the bundles you looked at, or
so let me go back to this, and then maybe I can answer this. So so where was this? So okay, so a gauge theory, it assigns to each manifold not just an actual vector space, but it assigns a vector space which depends on a bundle. So we can think of this as somehow a parametrized vector space, parametrized by the bundle. And when I said this, I didn't actually make this precise, but the way to make this precise is in fact the thing I wrote down there. So let's go back to down here. So where is this? So yeah, here. So the classical gauge theory, it assigns to each bourdism M. What does it assign? It assigns, first of all, the groupoid of G bundles, and then indexed by this groupoid, it assigns an object in wherever you're going to, in our case, vector spaces. And this thing is exactly an object in this span category. So an object in the span category indexed by C is just, first of all, a groupoid together with a map to C. So that's what, that's how this is in fact an object in here. And then if you have a bourdism between such, okay, let me maybe put this on a new page. So if you have a bourdism, if you have two manifolds M and N, and then you have a bourdism between them, then you can think of them as the manifolds as embedded in the bourdism as the boundaries. So this already kind of looks like a span, just somehow the other way around. So from this you get a span of the bundles. So if you take bundles on M, bundles on B, bundles on N, then if you have a bundle on B, you can restrict it to M. So that means that these inclusion maps, they give rise to maps going the other way. And now the gauge theory, what it does is it associates to each bundle. I guess I should have, to match the picture I drew before, I should have moved this a little bit. Oops, sorry. To each bundle, the gauge theory associates an object in your target category, for example, a vector space. And that's how you get this diagram. It associates to each bundle a vector space, to each bundle a vector space, and to each bundle here, it associates a linear map, which then you can all together put together in this natural transformation here. Yeah, so that's basically how this classical gauge theory goes from bourdisms to this fancy category of spans, which I really want you to think of as matrices, because I think that's somehow...
Yeah. Thank you for the clarification. So these span versus matrices, this seems to be a classical observation or so, but I see it popping up in all kinds of different places now. So Joachim Koch is pushing it to have his objective combinatorics.
Yeah, it's the same, exactly. Yeah, it's the same. Of course, this is a very elementary observation, especially if one looks at spans of sets. But then if one takes this seriously, it really motivates some math, which is quite interesting.
Yeah, then your talk. Then yesterday I read an article here by Google engineers.
Okay.
It appears in machine learning. So,
I see.
Yeah, it's quite interesting. Okay, thank you for the answer. So are there any questions, comments? Otherwise, I ask my vague question. Nicolas, please. Yeah, Nicolas.
So yeah, I have a vague question also. So at the beginning of your talk, you mentioned infinity n categories, and so n is the number of connected components of the border, so of your manifold, right?
No, n is the dimension. Sorry, n is
n is a dimension.
Yeah, so when I say n-1 manifold, I mean the manifold of dimension. Sorry, maybe this means manifold of dimension n-1. So so in so n is the dimension of the manifolds, and all this story which I was telling you about about Harper's result, it all only in the end produces this quantization in dimension 1. So for one-dimensional manifolds, which what it really means is you have zero-dimensional manifolds, so just points, and then one-dimensional manifolds, so just like lines and circles as bordisms between them. But of course, that's a bit unsatisfactory that this only works in dimension 1. But what I would like to convince you is that somehow this picture is very general and that one really should expect that this works in general. Yeah. But of course,
okay.
this is.
But so can you explain? I mean, I don't understand something certain is very basic, but what is the link between the dimension of the manifold and invertibility of the isomorphism? It's something I don't understand.
Okay.
Why
so
is
yeah, that's a good question. So let me maybe do this on a new page so that I don't get I don't mix up the notes. So I was a little bit vague on purpose on this because I didn't really want to delve into the whole infinity n category discussion, and I think the one categorical picture is already interesting enough. But so when I wrote board n, this is an infinity n category. What I really mean by this is the following. So these are really manifolds of dimension n all the way down to 0. So maybe let's draw it for n equal 2. So in board 2, what you really have is you have now my drawing skills are probably going to be tested, but you have so let's say no, I'm thinking how to draw this because I want to draw a picture, but I don't know how to properly draw it. So okay, so you have, let's say, 2 points and an empty set, and then this is now a one bordism from 2 points to the empty set. But now, sorry, maybe let's not go to the empty set, but let's maybe go to 2 points again. Let's maybe draw this picture. So this picture is a bordism, a one-dimensional bordism from the manifold which consists of 2 points to the manifold which consists of 2 points. But then there's another such bordism, which is just the identity. So let me maybe draw it a little bit behind. Maybe let me use a different color. Okay, so both the green and the black are morphisms from 2 points to 2 points. And now a 2 bordism will be a 2 morphism between these 2 morphisms. So now, I don't know if I can draw this, but there's a 2 bordisms, which is like a surface with boundary, which somehow, let's see how it looks. It somehow looks like this, and then, yeah, I don't know exactly. Yeah, it looks something like this. I hope maybe you can see the pictures. It's like a surface with like a lot of boundaries. So it's a surface with not just it's not just. So this is now I'm not just a manifold with boundary, but it's in fact a manifold with corners. It has these corners, and so this manifold we can now think of as. We have these 2 objects, then we have the green and the black, and then the orange surface is then a 2 morphism between them. So maybe I don't know, is this picture understandable? So this board 2, let me now spell it out. So board 2 has objects, 0 manifolds, 1 morphisms, bordisms between 0 manifolds. So these are then 1-dimensional. And then 2 morphisms are then bordisms between bordisms, which are then 2-dimensional. Yeah, and this is where it stops because we're in board 2. But you can see that more generally, if I put here board n, then I have n morphisms, which are bordism between bordism between bordisms, which are then n-dimensional. And then, of course, on top of this, I have like a whole hierarchy of invertible morphisms, which are just given by, you know, all the diffeomorphisms of all these bordisms involved. So then on top, we have all the diffeomorphisms plus then isotopies between these diffeomorphisms, isotopies between isotopies, and so on. But all this upper stuff, that's somehow all invertible. So that's why somehow, it's all
Okay.
So all together, so up to here we have non-invertible or potentially non-invertible, and also isotopies and so on, and all this part is invertible. So that's why altogether this is an infinity n category.
Okay.
Yeah, but thanks for asking, because this is a good question. Yeah, this is somehow, of course, very important if you wants to think about these TFTs. But yeah, of course, time is always an issue.
So I quickly ask my vague question. You started out somehow with you wanted to sum over stuff, yeah, but you never really specified what the meaning is. So, but in the end, you got an example you showed. You got some meaningful results, but in the intermediate step, you use the free object, yeah. And the free object, of course, is somehow cheating, because if you go free, you can sum up everything. Or apples and oranges, you can sum up in the free vector space over apples and oranges. So, but so
Yeah,
how is this? Yeah, where's the meat? Where's something happening?
I mean, the meat is in this map, because this map, it turns the free sum into an actual sum. Like, think of this as saying, right? Like, so let me just write a very simple analogy, just so as you said, right? Like, you take the free vectors, like, let's say you have a vector space. Then, of course, you can take the free vector space on all of its elements.
Yeah.
Something stupid like this. Now you have like all sort of formal sums, but then the identity from V to V induces a map here, which sends a formal sum of elements in V to the actual sum of V. And of course, this is where everything happens, because this is the map, which in order to have it well defined, you have to be able to actually sum in V. And
okay, so then C came already with all the information you needed somehow.
And this is, yeah, so this is the content of the theorem. So of this theorem of Harpas. Let me scroll back to that. It was a little bit fast, unfortunately. So the fact that how to say, the fact that this explicit construction, this span category, explicit maybe in the quotes, but like, it's at least something you can sort of write down with a bit of care, which is in fact the category which also appears independently as the target of this unquantized version. The theorem is that this is in fact the free one, because of course the free a priori could be something. Like, somehow the hard theorems are always when you exhibit a concrete object, which you can write down more or less explicitly. If you exhibit that as the free thing, then you have usually proven something. And in this case, what you have then proven is that the identity, so that then if C is already semi-additive, which of course is an assumption, right? Like, you have to show that your category C is semi-additive, for example, vector spaces. If this is already semi-additive, then since this is the free one, it will have a canonical map to it, which just sends, which just uniquely extends the identity.
Thank you. That really helped with the example with the vector space and the free vector space over it. Yeah, thanks.
Yeah. So this is somehow what's happening. Yeah.
Okay, great. So yeah, maybe unless there's other comments or questions, we're a bit over time already. So, but please feel free. Otherwise, yeah, thank you, Tashi, again. Very interesting stuff. And Yeah, I wish you all a happy, a good weekend. Yeah.
Yeah, you too. Thanks again for inviting me.
Thank you. Bye.